Okay, so let's finish the part concerning conditional expectation. Okay, so I will continue. What we have finished with. Okay. Okay, so in the previous session, I have defined the conditional probability mass function and the conditional density function. And we are going to see today that in order to define conditional expectation, of course, these two notions will be fundamental. And in fact, what we are going to do as computation is not very far. And in fact, it's totally equivalent to what we have done in order to compute expectations or in the discrete or in the jointly continuous case. Okay. So let's see the definition of the conditional expectation in the case where I have two discrete random variables. So I am in the discrete case here. So keep in mind that with the notation involved in the slides, that if I want to compute the expectation of a function of x in the discrete case, okay, I have a sum over the possible values of x of what? The value of my mapping multiplied by the probability that x is equal to small x. Okay, so this is the definition of the expectation in the discrete case. In the same way, if I have a pair of discrete random variables, if you want to compute the expectation of a function of x and y, you will have, in fact, a double sum to do here. It will be a sum over all the possible value for x and all the possible values for y of what? Of phi of xy. And then you have to multiply by the joint probability mass function. Okay. What it is important to remark here, and that will be a big difference with respect to what we are going to do after, is that here expectations are numbers. Okay, real numbers in this situation. Okay, and here I have a double sum that I can do in the order I want, okay, according to what I have said previously. Okay, so now definition of the conditional expectation. Okay, so I consider two discrete random variables. I denote R of x the set of the possible value for capital X, R of y the set of the possible values for capital Y, okay? And I consider that phi, that is a mapping from R square into R, such that, okay, but the expectation of phi of xy belongs to L1, okay? And in this situation, we are going to be able to define the conditional expectation of a function of x and y given x. Okay, so first of all, and it's something that is really important to keep in mind, contrary to what happened for the expectation, the conditional expectation is in general not a number, it's a random variable itself. And a random variable that takes a very particular form, that is to be psi of capital X. Okay, so this is the way you write a conditional expectation. In any situation, the conditional expectation given a random variable will be a function of this random variable. So it's a new random variable having some particular property. And of course, if I want to know explicitly what is this one, okay, I need to know what is phi of x. And typically in this situation, I need only to know phi of x for x belonging to the range of capital X. And what is this? But simply, okay, it's something that is not very far from what I have written here. It will be a simple sum here over the possible value of y of the mapping phi of x, y, multiply by what? So here I multiply by, so in the case of a single expectation with respect to a single random variable, it's the probability mass function of x here. Here it's the probability mass function of the pair. And here it will be the conditional probability mass function, that is the probability y given capital X equal to small x at the point y. Okay, so it will be a sum over y, okay, of these quantities, where here I have the conditional probability mass function of capital Y given capital X equal to small x. And we use a notation for this mapping here. This mapping phi of x is something that we denote this way. It's just a notation. I write it. Phi of x is, it's a notation defined as this notation. And why we use this notation? Simply because if I plug capital X inside, okay, I recover exactly what I need to have here. Okay. So maybe let's do an example of such a computation, an example we have already done together. Okay, so let's do the job here. I am in this slide here. I want a new page. Okay. So let's be in the following situation. So suppose that you have X that follows the Poisson of parameter lambda 1, that Y follows a Poisson of parameter lambda 2. Suppose that X and Y are independent, okay? We have seen together that given X plus Y equal to small n, belonging to n, we have seen together that Y follows in this situation a binomial distribution of parameter n lambda 2 over lambda 1 plus lambda 2. Okay? And what I want you to compute here, okay, is to compute the conditional expectation of y given x plus y. So be careful, because here, okay, you may do some confusion with my notations, okay, because I have defined the conditional expectation of x given y, okay, or y given x here. So let's do the job. So what is this? From the previous definition, I know that this is a function of x plus y, the random variable, okay, using for the conditioning. And what is phi in this situation? Phi of k is just equal to the sum, okay, over what? So it's the sum over the possible values of capital Y, okay, so n belongs to capital N, okay, of what? N time the probability of Y given x plus y equal to k at the point N here. Okay, so a priori, It's what I have to do. Okay, but we have remarked in a previous computation that when I fixed n, this, excuse me, okay, just in order to avoid some confusion in the notations, okay, I will just change to begin with the notation here. So in order to make not confusion between the things here. Okay, so I will put n here. Okay, so it will be the conditional probability of y given x plus y equal to n. And I will do the sum over a parameter that I will denote by k. It's in order to avoid confusion. Okay, and I do the sum over k belonging to n. So a priori, okay, it's what I have to do. But from a previous computation, we have seen that this one, this conditional probability mass function, is the one of a binomial of parameter n lambda 2 over lambda 1 plus lambda 2. So it means that here, what I have to compute, in fact, when small n is fixed here, is just the expectation of a binomial of parameter n lambda 2 lambda 1 plus lambda 2. And I know from the course what is this expectation. It's the product of the parameters in the case of a binomial. So I obtain n times lambda 2 over lambda 1 plus lambda 2. So I have computed explicitly this one in order to have the conditional expectation of y given x plus y. I just have to plug into this mapping, replace n by capital X plus capital Y, and so I obtain capital X plus capital Y multiplied by lambda 2 over lambda 1 plus lambda 2. So you see that here the conditional expectation is of course a function of mapping of x plus y, okay? And here this mapping is given by the expression in red, okay? So once again, and you will see that in most of the computation we are going to do, we have no more technical difficulties to compute conditional expectation than to compute expectation because, okay, we are going to use, as here for the binomial distribution, all the result we know about the computation of expectation in here classical discrete random variables. Okay, so I have this one in the discrete case. Okay, so I am here. So let's see now what happened in the continuous case. So in the continuous case, it's exactly the same thing. Okay, and you will just replace conditional probability mass function by conditional density function. So let's remind the same thing as previously. So you know that when you are in the continuous case, if you want to compute the expectation of a function of x, it will be an integral of what? Phi of x multiplied by the density function of x. If you want to compute the integral of a function of xy, when xy has a joint density function, so when x and y are jointly continuous, but here I have a double integral to compute. That is the double integral of the mapping f of xy with respect to the joint, it's an x here, the joint density function. And here again, I keep in mind that here I obtain numbers. Okay, expectations are numbers. So here, if I am interested in defining what is the conditional expectation of a function of x and y given x, once again, it will be a random variable that takes the form to be a function of capital X, where this function may be computed. So in the previous case, it was a sum. Here it will be an integral of what? Of phi of x, y with respect to the conditional density function of y given capital X equal to small x. And the integration here is with respect to the variable y. Okay, so you see that the small x that you have here is here and here. It's something that is fixed in the computation of the integral. So computing conditional expectation in this case would just be compute integrals. And this kind of integrals will be computed in general using what we know from, okay, the part of the course concerning continuous random variable. And once again, I use the same notation for phi of x, that is this one, the conditional expectation of phi of x, y given capital X equal to small x. Okay, so nothing new in this situation. Okay, just have a look on the fact that instead of computing sum as in the discrete case, we compute integrals. Okay, so nothing new for you. So let's have a look on a little example we have already done together. So together we have seen, okay, the example concerning the following. So if I start with a joint density function given this way, so exponential minus x over y, exponential minus y over y, indicator function x strictly positive, indicator function y strictly positive. Okay, we have seen together that when y is strictly positive, okay, we have seen together that given capital Y is equal to small y's, x follows an exponential of parameter 1 over y. Okay, it's a computation I have done in the previous video here. And my question is now, what is the conditional expectation of x given y? So from my previous definition, it will be a function of y, where this function is given by the integral minus infinity plus infinity x, because I have x here, multiplied by the conditional density function of x given capital Y is equal to small y, x dx. Okay, and I have to compute, in fact, this one for y strictly positive, that is the set of the possible values for capital Y. But once again here, okay, I have nothing to compute in my particular situation because I have already done the job. What is this conditional density function here? It's the one of an exponential of parameter 1 over y. Okay, and I know what is, so here, in fact, I just have to compute the expectation of an exponential of parameter 1 over y. And what is the result here? But I know that the expectation of an exponential of parameter lambda is equal to 1 over lambda. So here it's 1 over y, that is just equal to y. And at the end, my conditional expectation I want to compute in this very particular situation here is simply equal to capital Y. So it is a random variable here that is simply equal to capital Y. Okay. So you have here, okay, one example in the discrete case, one example in the jointly continuous one, okay. And in general, okay, when you compute a conditional expectation, or when you want to compute a conditional expectation, it is always possible to come back to the definition, and then you will have to compute sums or integrals, okay. That's why the computation of sums and the computations of integrals are a prerequisite for this course. So let's continue. What is nice is that, okay, we have interesting properties concerning the conditional expectation. For the expectation, we have properties. We have seen that, okay, the expectation is linear. We have seen that the expectation of a product is equal to the product of the expectation if we have independence or something like this, okay? In the case of conditional expectation, we are going to have also nice properties that are coming from the definition, okay? 5 statements that you have to know. The conditional expectation first is linear. That is, okay, if you want to compute the conditional expectation of lambda 1 y1 plus lambda 2 y2 given x. So the conditional expectation of a linear combination will just be the linear combination of the conditional expectations. So this is the linearity of the conditional expectation. So be careful here, there is a little mistake here. There is a mistake in the slide here. Instead of x, you have to put f of x here, not x. So what is the meaning of this result? The conditional expectation of a function of x given x, okay, is just by itself. That is, if x and y are independent, the conditional expectation of a function of y given x is equal just to the expectation. In the case of independence between the random variables inside here, the conditional expectation of a function of y is just the expectation. Conditional expectation and expectation coincide in the case of independence. Other nice property, that is, we have said that the conditional expectation is a random variable. So a priori, it is possible to take its expectation. If I take the expectation of the conditional expectation, I just recover the expectation of the random variable y here I have inside. So conditional expectation as an expectation equal to the expectation of the random variable y. And finally, okay, some other rules of computations, okay, that tell me that the conditional expectation of a function of x multiplied by a function of y given x is just equal to this function of x multiplied by the conditional expectation of the function of y given x, meaning that I can remove a function of x from the conditional expectation. In the case of the expectation, you can remove constant from the expectation. In the case of conditional expectation given x, you can remove from the conditional expectation any function of x. In fact, you can see that the statement 5 is in fact just a generalization of the statement 2. Okay, if you take g of y that is equal to 1, okay, you recover exactly this term here. Okay. So I have this one. Okay. So maybe I can try to prove some of them. A priori, if I want to be totally correct, And if I want to prove this proposition in grid generality, okay, I have to prove it for the two cases we have seen together. That is the case of discrete random variables and the case where we have jointly continuous random variables. Okay, so of course I won't do the job because I will have a lot of proof to do, but I will do some of them. And maybe let's say in the discrete case, why not? So it can be a very good exercise at home for you, okay, to try to prove these statements in the case where the random variables are jointly continuous. Okay, so let's do the job. So I will take a new page for this one. So first, I want to prove that the conditional expectation of f of x given x is just equal to fx. Okay? So what I know from the course, I know that the conditional expectation of fx given x is equal to a function of x, where phi of x is given by what here? It's a sum, okay, over what? But the set of the possible values for this random variable here, okay, the set of the possible values, that is just, okay, so here I have what? So f, let's write it this way, f of k belonging to, let's say, the set of the possible values for capital X, multiply by the conditional probability mass function, okay? So the conditional probability mass function of what? Of, let's say with my definition, y, okay, given capital X is equal to small x, y. Okay, so I just apply my result. Here I have a function of x and y that is very particular. Okay, I apply, so that is given by f of x. Okay, I apply this to my definition, okay, given by this slide here. Okay, I just apply here this definition with this sum here, just in the case where, in fact, instead of having a function really depending on x and y, I have a function only depending on x. Okay, so let's come back to what I have done here. That is this one. So I have done a mistake here. Okay, the mistake is that the sum has to be computed, okay, not over this one, but over the possible values for y. And here, I don't have a k, but I have here an x. So I have this one here. What can I do? I see that f of x doesn't depend on y, so I can remove it from the sum. And I have this sum to compute. Okay? But what is this sum? If I come back to my definition, okay, it's the probability that y is equal to y intersected with x is equal to x divided by the probability that x is equal to x. Okay? But what I will obtain for this sum here? So I obtain something divided by the probability that x is equal to small x, and I have a sum to do. That is this one. Okay, but what is this sum? So it's something we have already seen together, because you know that when you have the probability mass function of the pair, if you want to recover the probability mass function of each component, you just have to compute partial sums. And here, if I do the partial sum with respect to the values of y, I obtain what? Simply the probability mass function of x that I divide by the probability mass function of x, and of course I obtain 1. At this stage, okay, I can also do this remark that I have defined this one as the conditional probability mass function, and in fact it's really a probability mass function in the case that the sum is equal to 1. Okay, it's a remark that we can integrate. Okay, so at the end, in my computation, my psi of x is equal to f of x, and then, okay, my conditional expectation given x is just f of x, and it proves the statement 2 of my proposition. Okay, so if you have to compute the conditional expectation of a function of x given x, this conditional expectation is simply the function of x itself. So let's try to do another one. Maybe I would try to prove 2, 3, 4, and 5. Okay, so here, conditional expectation, I am interested in the conditional expectation of j of y given x in the case where, okay, I have independence between y and x. And my aim is to prove that I obtain in this case simply the expectation of j of y. Okay, so once again, I come back to my definition. I have this conditional expectation to compute. It will be a function of x where psi of x is given by, so I am in the discrete case, so it will be the sum over the possible values of y, of what here, by j of y, multiplied by the probability mass function of y given capital X equal to small x, y. Here, I have written nothing, just, okay, so if I come back to the definition was for a function of x and y, and here this function is just a function of y, so that's why I have this expression here. But what I know from my statement, I know that they are independent. And in the case where they are independent, we have seen together that the conditional probability mass function in this situation is just the probability mass function of y. And so this term is what? It's the sum over the possible values of y, of jy multiplied by the probability mass function of y, that is just simply what we call the expectation of jy. And I have my result. I use the independence just to say that my conditional probability mass function in this situation is simply the probability mass function of y. Okay, so I have proved the statement 3. Statement 4, to prove that the expectation of the conditional expectation is equal simply expectation of y. Okay, why not? So let's come back to the definition once again. So what is the expectation of y given x? First, I know that it is a function of capital X where psi of x is given by the sum y belonging to R y, okay, and here, okay, it's y p of y given capital X is equal to small x y, okay. So it's a function of x. So if I want to compute the expectation of the conditional expectation, it is just the expectation of phi of x. And I know from the course how to compute the expectation of a function of x. In the discrete case, it is a sum over the possible values of x of what? Psi of x, probability that x is equal to small x. So what I have to do now, I just have to plug this one here. And let's do the job. So I will obtain double sum of what? Y, probability y given capital X is equal to small x y multiplied by the probability that x is equal to small x. Okay, so I have this double sum to compute. But what I know from the definition of the conditional probability that this one is none other than, and that's why I have defined the conditional probability mass function. It is just the probability that x is equal to x intersected with y is equal to small y. So here I just have the joint probability mass function. Okay, it's the joint probability mass function. And I have to compute, in fact, the double sum of a function of x and y that here is just a function of y, but multiplied by the joint probability mass function. By definition of this one, it's the formula that I have reminded here at the very beginning. Okay, so let's see this one here, okay, with integral. So I have reminded to you at the very beginning of this session that when I have to compute this kind of expectation, okay, it's a double sum with respect to the joint probability mass function. It's exactly what I use here in the case where this one is just capital Y, that is that here I have just small y inside, okay? And so if I come back to what I want to do, that is my computation here. Here I recover simply the expectation of y, simply, okay? So I have proved that the expectation of the conditional expectation is equal to the expectation of the random variable itself. So last statement here. Okay, so I want to prove that under good conditions, the conditional expectation of f, x, j, y given x is equal, it's what I want to prove, is equal to, but I can remove what I know. That is, if I am given x, I know x, so I can remove a function of x from the conditional expectation. So let's do the job. Okay, so once again, I have no choice then to come back to the definition. So what is this one? This is by definition a function of x, where psi of x is given in this situation. So by a sum over possible value for y of f x j y multiplied by the probability mass function of y given capital X equal to small x at the point y. So it's this one that I have to compute. But if I do the job here, what I obtain, I have a term here that doesn't depend on y, so I can remove it from the sum. And then I obtain this term. But I recognize this sum. This sum here is none other than the one I have defined as the conditional expectation of j y given capital X is equal to small x. So now, if I want to compute this one, I have to do what? I have just to plug capital X here. And if I plug capital X inside, I obtain f of capital X multiplied by the conditional expectation of j of y given capital X. And I have my result here. Okay. So I have done the proof of the proposition, at least for 2, 3, 4, and 5. For small one, it's a little bit more complicated to prove the linearity this way. Okay, it's possible, but a little bit complicated. So I won't do the proof, but I want you to know the result. A very good exercise for you should be to do exactly what I have done for 2, 3, 4, and 5 in the case of jointly continuous random variable. That is not to handle sums, but in order to handle integrals. You will see that the proofs are exactly the same, okay, but it's a nice way to handle the definition of the conditional expectation in the jointly continuous case. Okay, so I have this one. Before to continue, I want to give you, because, okay, what I have done, I have given to you definitions of conditional expectation in both discrete and jointly continuous cases, okay? But I want to give you now an intuitive interpretation of the conditional expectation. What is this from an intuitive point of view? It's something that is important to have in mind, okay, if we want to give some intuitive aspects. Okay, to do this, I will remind you what we have done in the list 4 of exercises, okay? In the list 4 of exercises, we have seen together that if I want to minimize this quantity, we can see together that if I want to minimize this quantity, the minimum of this quantity is the variance of y, and the point at which the minimum, so argmin, is just the point for which the minimum is reached, okay? So the point where I have the minimum here, we have seen that this is the expectation, and that's why I obtain the variance this way. And what was my conclusion for this one? I have argued that I can consider the expectation of y as the best approximation of y by constants. Okay, I have explained to you this in a previous session. Now, what we are going to do is not very far. What we are going to do now, here we are going to looking for the minimization of the expectation of y minus a function of x. So it's the same quantity, okay, but instead of wanting to minimize with respect to constant, I want to minimize with respect to, I replace c by a function of x. So in particular, I have, if I am a function of x, I can be a constant, okay, for sure, but I enlarge, if you want, the set of the points. Okay, so I want to minimize this quantity and see what happens. Okay, so let's do the job. So first, from a result we have seen previously, I can say that this expectation I want to minimize is equal, from the last result I have proved, to the expectation of the conditional expectation. Okay, the expectation of a random variable is equal to the expectation of its conditional expectation. It's what I have proved at the end of the previous proposition. Okay, so here I have something by definition that is a function, okay, that is a function of x, because it is a conditional expectation given capital X, where phi of small x is given by, okay, by the notation here, the conditional expectation of y minus phi of capital X square given capital X equal to small x. And here, if I know that capital X is equal to small x, I can just plug inside this one. Okay. If I want to minimize this quantity now, okay, here I have a random variable, and now I have here something that is a number. It's not a random variable anymore, through this little trick here. So if I want to minimize this one, I said that this one is minimal for what? In fact, I can use the analogy with what I have done previously. In the case where I am interested in the expectation and by approximating by constant here, the minimum, okay, is obtained for the expectation. Here, okay, I want to approximate y in the same sense with the difference of the square here by things that are in fact constants, particular constant, but constant here. And by analogy with this case, phi of x is minimal for what? But not the expectation, but for just the conditional expectation of y given capital X is equal to small x. Okay, so I use the analogy of this term here, where I have the approximation of y by a constant. So it is given capital X is equal to small x. But if I do the analogy with what I have obtained here, minimal for this term. Okay, it means that I can have an interesting approximation, intuitive interpretation of the conditional expectation. And I can write the following that you need to have in mind, that the conditional expectation of y given x is the best approximation of y. So expectation is the best approximation of y by constant here, but by here functions of capital X. So if you enlarge, okay, the set of the possible approximation passing from the constant to the function of x, but the best approximation becomes the conditional expectation. So the conditional expectation of y given x is the best thing you can do if you want to approximate y by a function of x. If you want to approximate y by a constant, you will use the expectation. If you want to approximate y by a function of x, you will use the conditional expectation of y given x. Okay, so conditional expectation that can seem to be abstract with respect to the definition I have given to you that are maybe coming from nowhere, have in fact a strong intuitive interpretation. Okay. So let's finish the course with 2 definitions and 1 proposition. So I have defined here the conditional expectation. Okay. I will be able to define the conditional variance. So here, once again, you know that if I want to define the variance, I need to be in L2 because the variance of y is equal, so I have 2 equivalent definitions, is equal to this one, that is equal to the expectation of y minus the expectation of y square. Okay. So the variance is this one. And if I want to give sense to this one, I need to give sense to these 2 terms. So for this one, y has to belongs to L1. Here, y has to belongs to L2. I know that L2 is included in L1. So if I want to give sense, okay, for y in L2, it works. But it's exactly the same for the conditional expectation because I have defined the expectation for random variables in L1. And I defined the conditional variance this way. So I have defined the variance as the expectation of the square minus the expectation of y, excuse me, here, square. And for the conditional variance, it will be the conditional expectation of the square minus the square of the conditional expectation. Okay, so this is a natural extension of what I have written here, replacing expectation by conditional expectation. And as we have this equality here, we have in fact the following equality, that the conditional variance can also be expressed this way. So we are going to do the proof of this one because a priori it's not that easy that I have the equality here. Okay. So let's work with the conditional expectation of y minus the expectation of y given x square, okay, given x. So what can I do? I don't have the choice. I can just develop the square and see what happens. So I have y square minus 2y expectation of y given x plus the expectation of y given x square given x. Conditional expectation is linear. So in fact, I have 3 terms. The first one being this one, no problem. The second one being, so I have linearity, so I have minus 2, conditional expectation of y, conditional expectation of y given x, and plus the last one, that is the conditional expectation of y given x square given x. So what can I use now to continue? So for the first term, okay, so no problem, it will be this one. That will be exactly the one involved in this first definition here. And what happened for these two? Here, keep in mind that I have a function of x. So from the previous proposition, I have a function of x that I can remove from the conditional expectation. Here, the same. This one can be removed. So this term is equal to what? Is in fact equal to minus 2 conditional expectation of y given x multiplied by the conditional expectation of y given x. And here I obtain the conditional expectation of y given x square multiplied by what? By the conditional expectation of 1. Conditional expectation of 1 that is just equal to 1 because the conditional expectation of a constant is a constant here. For sure. Okay. And at the end I have what? Here I remark that my term here is equal to minus 2 conditional expectation of y given x square. So this term is this one. If I do the sum of this term and this one, I obtain simply this one here. Okay? So I have proved that I have this equality here, that the conditional variance of y given x is equal to this expression. Okay? So I have this one. And in particular, if I come back to my previous page, here we have seen that, okay, the best approximation of y by a constant is given by the expectation, okay? The minimum of this quantity is given by the variance. So the minimum is at expectation of y. The minimum of the objective function is the variance here, okay? Here, if I do the same, the conditional expectation is the best approximation of y by function of x, okay? And the minimum of these quantities here will be obtained for, in fact, so if I replace phi of x by the conditional expectation of y given x, here, I obtain here the expectation of the conditional variance of y given x. So in this case, I have said that my best approximation by a constant is the expectation. The quality of the approximation is given by the variance. If I do the same for the approximation by function of x, the best approximation is given by the conditional expectation. And if I plug inside this one, okay, I obtain the expectation of the conditional variance of y given capital X. So this is something here, the conditional expectation of, and the expectation of the conditional variance will be a quantity that will measure the quality of my approximation by a function of x, of my best approximation. If this one is small, it will imply that I have a very good approximation or a good approximation. And if it is large, that I will have a bad approximation by function of x. So let's continue, okay? And now we are going to, so excuse me, so to give a last definition, that is in fact the last proposition that we are going to prove. So I put this one here. So I erase everything here. Okay. Tac. Proposition that tell me that the variance of y, so I have a very nice proposition, that is proposition 24 here, that tell me that the variance of y is equal to the expectation of the conditional variance plus the variance of the conditional expectation. Okay? So we are going to prove this, and how to prove this, but we are going to start from these two terms and see what happened. Okay? So for this one, what is the expectation of the conditional variance? The expectation of the conditional variance, so let's replace by the definition of the conditional variance. It's the expectation of what? Of the conditional expectation of y squared given x minus the conditional expectation of y given x squared. By linearity of the expectation, I obtain the expectation of the conditional expectation of y squared given x minus the expectation of the conditional expectation of y given x squared. And here, I know from the previous proposition that the expectation of the conditional expectation is just the expectation of y squared here. Okay? So this is for this first term. For this second term here, I am interested in the variance of the conditional expectation. So what is the variance? It is the expectation of the square minus the square of the expectation. But what is this term? I know that the expectation of the conditional expectation is the expectation of y, and I have the square here. And you see that when you do the sum of these two terms here, when I do the sum of these two quantities, what I have simplification between this term, and I obtain the expectation of y squared minus the expectation of y squared. Okay? So I am in the situation where I have proved my proposition 24. Okay, I have proved my proposition 24. So last things I want to say to conclude this part of the course. That is to introduce a notion that is often used in statistics, okay? That is the notion of the R square. The R square that is equal to what? So it's the variance of the conditional expectation of y given x, it's a definition, over the variance of y. okay, over the variance of y. So just a remark. So from the proposition 24 here, I can replace the variance of the conditional expectation using this relation here. So I obtain what? If I do this, I obtain 1 minus the expectation of the conditional variance over the variance of y. Okay? I have this one. And from this one, I can see that my R square is something that is between 0, so 0 because it's a ratio of variance, and less than 1 because here you have something that is positive. So you have something that is between 0 and 1. This R square is a number between 0 and 1. Okay? And we are going to see here what happened in, okay, the two limit situations. So what happened if R square is equal to 0? So if R square is equal to 0, okay, then what I have that the variance of the conditional expectation is equal to 0. And so if a variance is equal to 0, it means that the conditional expectation of y given x, okay, is equal to what? To its expectation. It is equal to its expectation. Okay, it is a constant and equal to its expectation, the classical result with respect to the variance. A variance is 0 if the random variable is always constant, equal to its expectation, of course. So this one is equal to the expectation of the conditional expectation, that is just the expectation of y. And what is the meaning of this one? Okay, so if you consider conditional expectation as the best approximation of y by function of x, in the case where the R square is equal to 0, it means that you have a very bad approximation. Bad approximation. Why bad approximation? Because what you can obtain by approximating y by function of x is the same thing that what you can obtain when you approximate y by constants. So approximate by constant or approximate by function of x, it's exactly the same thing, meaning that to enlarge the set of the approximation give you absolutely nothing more, okay? So when my R square is 0, the conditional expectation of y given x is in fact a bad approximation of y by a function of x because it can't do better than what you do when you approximate with constants. Okay? So it's the first case. If R square is equal to 1, if R square is equal to 1, okay, it means that that's what? Okay, so I have R square equal to 1. So it means that in this situation, okay, the variance of y is equal to the variance of this one. Okay, so the variance of y is equal to this one, implying that so the variance of y is equal to the variance of the expectation. Okay, so when I am equal to 1, and so the expectation of the variance here is equal to 0. Okay, but so I'm sorry, I have some noise because I have some, okay, I have a road, okay, near my room, okay, and you have, as in the Boulevard de l'Hôpital, you have cars, okay, you have workers, so you will maybe find a little noise that is not pleasant, okay, but it's because you have a road near my place, okay? So sorry for that, but I can't do anything. The only thing I can do here is that I don't have to open the windows because I am alone, okay? I don't have to put the mask because I am alone, so it's better than in the Boulevard of l'Hôpital. Okay, so I have the expectation of the variance that is 0, but the conditional variance here is something that is a positive mapping here, positive mapping. And so it implies that the variance of y given x is equal to 0, implying what? Implying, so if I come back to this definition here, it implies that y is equal to the conditional expectation of y given x. And what is the meaning of this one? But here, it means that I am in the best case. So which best case? So keep in mind that in the situation where I want to approximate y by function of x, okay, I am in the best case because here, when r squared is equal to 1, it means that y is itself equal to its conditional expectation, meaning that it is a function of x. So if I want to approximate it by function of x, I am in the best situation, but because the approximation will be perfect in this situation. So when the r squared is equal to 1, I am in the best situation if I want to approximate y by function of x. That is the situation where y is itself a function of x. Okay, so when r squared equal to 0, the worst situation in function of x, when r squared is equal to 1, the best case because y is itself a function of x. Okay, so I will just finish. So the program concerning conditional expectation here is finished, but I want to do a little something that can be considered an extra part of this this course, okay, concerning conditional expectation. So I want to discuss, okay, about what we call best or optimal linear predictor. Okay, so expectation is the best approximation of y by a constant. Conditional expectation of y given x, the best approximation of y by a function of x. Now, my aim will be to approximate, so my job, okay, what I want to do is approximate y, not by constant, not by all the function of x, but by very particular function of x, by functions of x of the form, but affine function of x, in fact, that is of the form a plus bx. Okay, so I want to approximate the best I can y by function of x of the form here a plus bx. Okay, and for this best approximation, I will denote it by E star of y given x. So it will be something that will be more precise than the expectation, okay, because it includes expectation, taking b equal to 0. but it will be something that will be in general less precise than the conditional expectation, because for the conditional expectation, you approximate by all the mappings depending on X. Here, very particular mappings that are affine one, okay? Affine. Okay, so I have a program of optimization to solve here. So I want to find what I have said here, something that will be an affine function of X that I will denote by alpha plus beta capital X, where I want my alpha and beta to be optimal in the sense that the pair alpha beta is the one that will minimize. So which quantity? But the same as previously, that is the expectation of, so I consider that I approximate y by a plus bx, okay? And I want to make this minimal in the sense of the expectation of the square, okay? If I have constants here, it's what I have done for the expectation. If I have function of x, it's what I have done for the conditional expectation. And here I just take a affine function of capital X. Okay, and I can denote this one by a function depending on two variables. And what I want to do here, I want to minimize a function depending on two variables. So you have a course of optimization. So I hope that you are, for most of you, okay, you have a course of optimization, and I hope that you are able to minimize mapping depending on two variables. First of all, I have to solve the Euler conditions. Euler conditions. That is, okay, I have to consider the partial derivative of the objective function, and I want to make them equal to 0. So what is this, okay, partial derivative? So I won't enter into all the details of the computation because they are very, very basic. So what I do, I develop the square here and I compute, so I obtain a polynomial of order 2 in A and B. So it will be very, very simple to compute the partial derivative. And I obtain, in the case of the partial derivative with respect to A, 2 times the expectation of y minus A minus B x. And if I compute the partial derivative with respect to B, I obtain minus 2. So the minus 2 comes from the square here, okay? And expectation of x multiplied by y minus A minus bx. Okay? So what is the Euler condition? The Euler conditions means that if I want to find an optimum, I have to make this partial derivative equal to 0. And in this situation here, this system can be written in the following way, okay, very basically. A plus B expectation of x minus expectation of y is equal to 0. And expectation of x, y minus A expectation of x minus B expectation of x squared is equal to 0. So these two are equal to 0. And now what I have a linear system of two equations with two unknowns that it will be very easy to solve. And the solutions of this system, okay, here I will have a unique solution, will be, okay, my alpha and my beta that are the solution of my minimization program. So I can see, and you will do the computation at home, that in this case, my beta is equal to the covariance between x and y over the variance of x, and that my alpha is just equal to the expectation of y minus beta, the expectation of x. So I can express alpha and beta with quantities that involves only, okay, x and y as random variable, the expectation of x, the expectation of y, the variance of x, and the covariance between x and y. And at the end, my optimal linear predictor here is equal to what? So it is simply, okay, alpha plus beta x that I can express in a nice way as the expectation of y plus the covariance between x and y over the variance of x multiplied by x minus the expectation of x. Okay? And I can see from this one that if y is a constant, but the best linear predictor is, of course, the expectation, because the covariance term will be 0. And intuitively, if I am a constant, of course, my best linear predictor will be not the affine function of x, but just the constant. Okay, and I can also see that best linear predictors are something that is linear. So linear and why? But it's very basic to have this. Because if I come back to the formula, okay, here I have the expectation where I have y inside, so I am interested in the linearity of this in this variable. But I know that expectation is linear in y, and I know that the covariance is something that is linear, but here you have y only in one coordinate of the covariance. So by linearity, okay, or bilinearity of the covariance, you have exactly what you want, okay? So it was just a little exercise, okay? And so I have solved the Euler condition, okay? A priori, if I want, so from the Euler condition, excuse me, the only thing that I can deduce is that I have, in fact, here an optimum. I don't know if it is something that is a minimum or a maximum. In order to check if, we'll do it here, I have a minimum or maximum, okay, I have to deal with the matrix of what we call the Hessian matrix, that is the matrix of the second order partial derivative. Here, what I obtain here, if I compute the derivative with respect to A of the partial derivative here, I obtain what? I obtain 2 for this one. The one with respect to B, I obtain what? So with respect to B, I obtain, so if I compute once again, so the derivative with respect to A, it remains -2, okay. The derivative with respect to B here of this one is what? So I have -2 to expectation of X, 2 expectation of X. Here I will obtain also 2 expectation of X. Here, so that is the second derivative of f with respect to b, 2 times b. Okay, so I obtain what? Here I obtain 2 the expectation of x squared. Okay, I obtain 2 the expectation of x squared. And so what can I deduce here? I can deduce that this matrix, so if I compute its determinant, I obtain that the determinant of this one, okay, is something that is positive because it is equal to 2 times the variance of x, and the determinant here is equal to 2 times the variance of x. You have a determinant that is positive, implying that the matrix, the Hessian matrix, is a matrix that is positive, and in the case where the matrix it is positive, it means that I have a minimum. So that's why, okay, I obtain the minimum I want here as a best linear predictor. Okay, so the last part is not totally in the program of the course, but it's a nice exercise concerning, okay, handling optimization in relation with probability. So that's why I have done it, because I have time when I record videos. So see you for the next session, and the next session will be available next week, and it will concern, okay, random vectors and what we call Gaussian vectors. And you will see that we have links between the notion of Gaussian vectors and the one dealing with conditional expectation. So see you, and let's see you for the weekly live meeting that we will have on Thursday morning. Bye-bye.